I've developed a game analyst that records game videos and highlights the best and worst moves for each player. It accomplishes this by tracking players, classifying their moves, and can be easily adapted for other games and even competitive sports in general. Essentially, the idea was to design an architecture that functions with any video featuring multiple objects and can classify the actions each object takes. All it needs for training is a specific number of user-generated sequences. So what exactly is a sequence? A sequence refers to a predetermined set of frames or commands that a character executes upon a button press. This concept is typically hard-coded into fighting games, making sequence classification relatively straightforward due to minimal variations across multiple matches. For instance, pressing the K key triggers a prolonged heavy attack sequence in Brawlhalla, while the J key initiates a briefer light attack. Therefore, sequences can vary in length, a factor we must consider. While there's ample documentation on how to utilize sequence classification tools, real-life examples, particularly in the gaming domain, are rare. When implementations do exist, they often rely on training classifiers using individual video frames or focus solely on videos with a single tracked object. And classifying sequences in games has its own issues. So why use Brawlhalla for this? Well, except for being one of the most popular fighting games on Steam for a long time, it has a lot of complexity to account for. This includes moving platforms, swords being thrown, gauntlets being thrown, spikes being thrown. Wait, I see a pattern here. So here's the plan. First, we record the game and use a tracking algorithm to follow all characters. From this, we'll create a training set to determine which character it was. Next, we'll use a second classifier to identify each character's moves. While this is happening, we'll also keep an eye on the health bars. This will help us see if a move missed the opponent, correctly hit the opponent, or it got punished due to execution at the wrong time. With this information, we can figure out how effective each move was and count how often we hit, missed, or made a mistake. To track all moving characters, we can go with two popular background subtraction techniques: mixture of Gaussian and Gaussian mixture-based segmentation methods. They're pretty similar, but the segmentation method throws in some Bayesian decision-making to deal with noise. This means that the segmentation method takes a bit more computing power and runs slower than the mixture of Gaussian method. In this video by Mare Arts, it's pretty clear that the mixture of Gaussian method starts outperforming the segmentation method early on. This matters for us since our sequences might only last for 20 to 40 frames, which is less than a second. So we are going with the mixture of Gaussian method. So let's see how well it performs. Unfortunately, there are many background images mixed in with the character images. Therefore, we need the classifier to predict not only which character it is, but also whether it belongs to the background or is a spawned object. So 30 minutes later, I have a little bigger data set. It has 1000 images for the character classes and about 2000 images for the background class. Now we can start looking at some neural network code. The neural network that I'm using for object classification starts by using filters to pull out specific information. The filter currently displayed seems to amplify the brighter pixels, especially when surrounded by darker ones. Each convolutional block contains 32 of these 3x3 filters. Next, we employ max pooling to downsize the filtered image, taking the highest values from across the image. My use of max pooling shrinks the size by half in both dimensions, boosting processing speed and reducing the risk of overfitting. We run this process 3 times because we have 3 blocks in our model. Given our goal of classifying objects as background, so class 0, val, so class 1, or Ragnir, so class 2, we need to flatten the image into a one-dimensional format. This then gets converted to a 1D vector for the final layers. Following that, we introduce a dense layer with 64 fully connected neurons. This reshapes the data based on the output of a single neuron in that layer. Before our last step, we incorporate a dropout layer to randomly set some values to 0. This helps curb overfitting, though it might extend the model's convergence time. To wrap it up, we use a single neuron to determine the object's class. So let's see how the model performed. Okay, so an accuracy of more than 99% with a loss value of less than 0.1 is quite good. So let's see how it performs on the test set. Okay, 99.95% is definitely good enough for our purposes. Now we can finally start thinking about sequence classification, our final stop before creating the deep learning analyst. But there's a little issue. Usually while classifying images, there are tens of thousands of images used for classification. For example, the MNIST dataset for classifying handwritten numbers contains 60,000 training images and 10,000 test images. And the CFAR10 dataset for representing 10 classes of objects contains 50,000 training images and 10,000 test images. For my purposes, it took me around 10 minutes to generate 100 sequences. So spending 15 hours extracting tens of thousands of sequences per class is definitely something I do not want to do. So the solution is data augmentation. It consists of changes in brightness, rotation, contrast, saturation, cropping, blurring, padding, translating along X, translating along Y, flipping, adding noise, and some nice background replacement. For our cases, after we finish subtracting the initial background, the most important augmentation techniques are blurring, sharpening, flipping, zooming, random object addition, and also some nice background replacement. So with this, we can increase the efficiency and accuracy of the model by quite a bit much quicker. So now that we have our augmentations, let's look at some code. The initial code is pretty similar to the object classification code, except for the fact that it now says time distributed as a prefix. Well, that just means that it is modifying every image in a sequence in the exact same way. What we need to discuss though is the long short-term memory layer. As opposed to a CNN, an LSTM has cells or memory units that correspond to the dimensionality of the LSTM's internal state. So if I have a sequence of 20 images and an LSTM memory unit number of 256, this means that for each image in the sequence there are 256 memory units to remember pieces of information to help train the model. Higher memory unit or cell numbers means that the model can remember and analyze more complex patterns across the sequence. So when I started this project, I definitely wanted to minimize the training set required. Hence, we will first start with just one sequence across each class and add 50 augmentations for training the sequence classifier. Let's see how well it performs. Now for the testing part. Oh, looks a little useless because it seems that it repeated the same prediction across the testing sequences. Let's try the same with 5 unique sequences. Let's see how it did for the test set. That's much better, but it only predicted half the classes correctly. Well, looks like we just need more unique sequences, unfortunately. Okay. So it has been 8 more hours and I've generated more than 1,000 augmentations for the 20 unique sequences for each class. This is the final attempt. If this does not work, I might have to abandon this project. Oh well, I guess I'll see you in 20 hours. So it has finished training at 99.5%. And a loss value much better than the previous ones. Countless failed combinations, numerous punished moves, a ton of games lost, hours of data preparation, and almost a day of training. It all comes to this. If this doesn't work, I have no video and this project has officially failed. Well, that looks pretty good actually. A couple of mistakes here and there. But 4 out of 118 means a 97% accuracy. This isn't bad at all. So since the classifier performed so well on the existing test set, we can play some new matches and see how it performs.
Welcome to Brawlhalla! 3, 2, 1, brawl!
And it unfortunately looks like I need to work on my sword side sig.
3, 2, 1, brawl!
Thirteen missed moves. Amazing. Well, to be honest, Brawlhalla was definitely not the best game to try this on because it has way too many characters and each character has 33 moves, excluding item throws. And I definitely should have tried it on some other game with much smaller complexity. But I hope you had fun, and with that, ladies and gentlemen, I wish you a good day and I'll see you next time.